Hey everybody, this is Dr. Johnson, and this video and its follow-up, video number 2, are focusing on process analysis and improvement. This follows on our discussion in our last class meeting where we were looking at process design and diagramming a process using flowcharts. So this is a flowchart of our case process, the Hopewell Hospital Pharmacy prescription preparation process, one version of what that flowchart might look like. And you can see in this diagram that we have both green colored steps, and then we also have some blue things. So all the steps that are colored in green are the steps that comes directly from our case, right? So we've got steps 1, step 2, 3, 4, 5, 6, and 7. So all of those come directly from our case. I've added here decision diamonds. So in each step where there's a decision that needs to be made, immediately following that step, we've got a diamond, right? So we've got those here. Also added a couple of additional steps that are implied in the case but are not directly addressed. But as we diagram it, we find that we need to add these steps. One of those is actually canceling an order when that's appropriate. And then another one is beginning at the very early part of the process, and that's the physician writing a new prescription. So in addition to that, in each of these steps, I've added a couple of things. One is the time, and another is the capacity for each step. So the time, again, comes directly from the case, and each of the steps, steps 1 through 7, have a specific time. Step 2, we can see here, is 1.3 minutes. And then each step we can calculate based on that time the capacity related to that step. And for step 2, again, the capacity would be 46.2 prescriptions per hour. Let's talk about what capacity means, and then we can come back to looking at capacities here in this case. So how do we calculate process capacity? So we can calculate our capacity for the entire process or for individual steps in a service process using this formula. And when we're talking about capacity, really all we're talking about is the maximum rate of output per unit of time in a particular process. So our capacity here, to calculate it, would be we'd need to know the number of servers that are available for executing the process. And then for this particular case, we're going to standardize around an hour. So how many prescriptions per hour can our process produce? What the maximum rate of output would be. So we're going to standardize the time required in minutes to an hour. And so our full formula then looks like this. Capacity equals the number of servers available times 60 minutes divided by the time required, the minutes required for each step. So if we take that formula then and apply that to the times we have in a particular step, looking at step 1 requires a half minute to do that step. Only takes a half minute to do that step. So if we take that and if we assume one server, if we take that time then, take one server's time, 60 minutes divided by half a minute, that would give us 120 prescriptions per hour. The capacity of this particular step, the maximum output for that step with one server is 120 minutes per hour. We can apply that same formula to each of the remaining steps and get capacity for those as well. If we look at step 2, the time for that particular step is 1.3 minutes. The capacity, if we put it into that formula with one server, is 46.2 prescriptions per hour. So we can begin to see that there's an inherent problem in the way this process is designed. We can do 120 prescriptions per hour through the first step, but only 46 through the second. We can continue to go there and see variations in each process step, and that, of course, begins to create some problems for us, and we'll come back to that in a few minutes. In addition to calculating the capacity for each individual step, we can calculate it for our entire process. So to do that, we need to first understand what is the time required for to get a single prescription through the entire process. And we've got that calculation down here. All we're going to do is add up the different the times for each step, and that takes 9.7 minutes. That's assuming that there is no rework. And for example, this rework right here with the prescription having to go back to the physician to rewrite it. So assuming no rework and everything goes fine, we've got 9.7 minutes per prescription. If we're to calculate the capacity for that, the total process, we've got our total process capacity calculation down at the bottom here, again assuming one server. So we've got 60 minutes divided by 9.7 minutes, and that tells us that we can get 6.19 prescriptions filled in an hour through this process, and we'll round that off and just say 6 prescriptions. So our process as a whole can process 6 prescriptions per hour. The maximum here, number of prescriptions per hour through an individual step, is 120. So we've got a discrepancy here, and for one server only being able to fill 6 prescriptions per hour, you can imagine in a hospital pharmacy that's not going to be sufficient. We're going to want to improve this process, and how can we do that? Well, we could certainly add additional servers, right? We could add additional pharmacists to do these steps, and by doing that, adding another server, we would double the number of prescriptions we could fill in an hour from 6 to 12. We could triple it by adding a third server. That would give us 18 prescriptions per hour. But that starts to get really expensive, right? Hiring additional people, especially people at the skill and competency level of the pharmacist, begins to get super expensive. So are there things we can do to improve the efficiency of this process without hiring additional people to do it? Let's think about that. So one of the tools we can use to begin to continue to analyze this process is a histogram. So what we've done here is just taken each individual step, steps 1 through 7, and put in a spreadsheet the time that is required for each step, and produce this histogram using Excel. And we can see that just as in the flowchart, where step 1 took a half a minute, here it takes a half minute, and we've got a visualization of the comparison of those different times for each of the steps in this histogram. And we can immediately see that step 5 takes a lot longer than all the other steps. Steps 2 and 3 take quite a bit longer than steps 1 or 4 compared to those surrounding steps. And step 7 takes quite a bit longer than step 6. So we can see there's a lot of unevenness here in terms of the amount of time it takes for each step. But let's back up for a minute and talk about some principles related to lean operating systems and how they might be helpful in thinking about process improvement. So when we're talking about lean operating systems, there are 4 objectives that we want to accomplish simultaneously to have a true lean system. The first of those is eliminating waste. So when we're talking about lean systems, we're thinking about eliminating waste, but we're also talking about, at the same time, improving speed, the process speed or customer response time. We're also talking about improving quality, and at the same time, we're talking about reducing costs. So in a lean system, we want to try to accomplish all of those things at the same time, not just one, but all of them simultaneously. Let's focus on making sure we're clear on 2 terms here that we've talked about before in class, but let's revisit our definitions. So waste and quality. When we're talking about waste, this is what we're talking about. We're talking about any step or activity that does not add value to the product or the service. In other words, the customer is not willing to pay for it, right? If we're doing something that the customer is not willing to pay for, that is a form of waste. When we're talking about value, we've got to go back and look at value here, right? Because that's integral to our definition of waste. And we've been talking about value from the beginning of the semester. Value is, we can think of it in terms of this formula, perceived benefits divided by the price or the cost to the customer. And then quality, again, is simply meeting customer requirements or expectations. So thinking about waste, value, and quality, let's go to now some specific types of waste that we can think about when we're looking at the system from a lean perspective. So lean operating systems gives us 7 types of waste. We've got overproduction, which is simply producing more than the customer needs, right? If we produce more than the customer needs, let's think about that in terms of a restaurant. If we produce more meals than are ordered, we're going to have excess food laying around that we're probably going to have to just throw out or donate somewhere. But either way, that is cost to us that we're not getting a return on, right? We've produced inventory that we're not going to be able to sell. So overproduction is a form of waste. Waiting time, that can be customer waiting time or waiting time within the system. So we've got workers who are waiting for material or inventory to come out of the step that precedes them, and they're just hanging out. We're paying people to hang out. That's not a particularly efficient use of our payroll. Movement or transportation, so that's moving materials around inside the process. Again, if we're thinking about a restaurant as a service and also a production process, we've got we've got raw materials or ingredients for a meal that are being moved around the kitchen. The more movement we have, the more waste we have in the system. There's obviously going to be some movement, but we want to make that movement as efficient as possible. Overprocessing, that means just doing more than the customer requires or expects from us. So let's think about a different production process. Let's think about making cars. And let's say we're painting the inside of a bumper to match the same color that's on the exterior of the car. Well, as a customer, I probably don't care a lot about what the color of the inside of the bumper is, because I'm never going to see that. So what I'm more concerned about is the color on the outside of the bumper matches the exterior of the car, the trim of the rest of the car. So if I as a manufacturer am painting the inside of that bumper, I am wasting time and money on both the materials, the paint, to paint the inside of the bumper, as well as the labor to do that work. So overprocessing. Inventory. Inventory, most systems, and we can go back to our discussion of push and pull, in any push system, we're going to have inventory in that system. The advantage of a pull system, as we've discussed earlier, is that there's very little inventory inside the system. So inventory can be a form of waste, but any push system is going to have some measure of inventory in it. What we want to do is minimize the inventory while still enabling ourselves to meet customer demand. Motion is people motion inside the system, so that's different from movement. Movement relates to the material movement. Motion relates to people movement. Again, we're going to have some movement or motion inside the system, but to the degree we can limit that motion, we're going to improve the efficiency of our process. And then finally, rework or production defects. Anytime we have to redo something inside our process, that is also a form of waste. These Japanese concepts or terms will be useful for us as well. Muda, and I'm not going to pronounce these correctly, but muda is just the Japanese term for waste. Murray is a term that we'll use for talking about being overburdened or overburdening or placing unrealistic expectations on a person or machine. And we'll also use this term mura or unevenness. So muri, overburdening, mura is unevenness. And we're going to focus on these 4: waiting time, rework, overburden, and unevenness as we analyze our process. So where do these 4 types of waste exist in the prescription preparation process? Waiting time, rework, MRE,